Welcome to our Arctic Speaker Series and our October, it is October, right? Yeah, our October talks. I'm really happy to continue this practice that we started a couple years ago of having the students who've been supported by the Northern Scientific Training Program come and tell us about their work. And what I'm going to do is I'm going to introduce everybody up front, and then when you come back up, just remind people who you are, okay? Because otherwise it gets a little tedious. So today we have from the Department of Ecosystem and Public Health, Andrea Hanke. From the Department of Geography, Araleigh Cranch. Sorry, maybe I should put my glasses on. Also from the Department of Geography, Samantha Jones. And again from the Department of Geography, Zoe Walker. We have three other students that couldn't be here today. Naima Jutha from the Department of Ecosystem and Public Health, Vinay Rajdev from the Department of Geography, and Andrew Clark, also from the Department of Geography. And so just for those who might be watching this on YouTube, we do have students that work in the Arctic and the North in places other than geography and ecosystem and public health. They're just not here today to speak to us. So I guess without any further ado, actually one thing I wanted to say is that the nice thing about these talks is they really highlight sort of the breadth of research that's going on in the university and amongst the students at our university. And even though we have a lot of geographers in the room, as you'll see, there's quite a lot of variation in the work that they're doing. So with that, I'll ask Andrea to come up and take it away.
All right, hi everyone. Before I get started, I'd just like to acknowledge that we are on the traditional homelands of the Treaty 7 people. And as already mentioned, I'm Andrea Hanke, and I have the pleasure of working with this fabulous group of people that I've listed at the end here, with Dr. Susan Coots here. And my research has been looking at traditional knowledge of the Dolphin Union caribou herd. And today I'm just going to show you some fun results I've had that have insights into behavior, population, and health status. So before we go any further, I'd also like to lay down the foundation of different ways of knowing. So with more indigenous ways of knowing, it's more holistic in that the animals rely on the people, rely on the environment, and that as one thing changes, the whole system will change. Meanwhile, in a more Western way of knowing, it tends to be more categorical. So when we're understanding things, it's looking specifically at a caribou, for instance. So what often happens is humans end up being separated from the environment and from the animals so that we can manage an outcome. So for instance, manage the conservation of a caribou. So this cute guy is what I get to learn about. This is the Dolphin Union caribou herd. And they're located within that red circle there. So they spend their summer on Victoria Island, the more northern part of it, and then migrate down across the sea ice to the mainland for the winter. And in these two communities, in Kulaktuk in Cambridge Bay is where I've been working a lot in right now. And they rely a lot on the Dolphin Union caribou herd. They're a very important species, not only for the environment, but for cultural and social reasons. They're currently listed as special concern by SARA, but COSEBEC has also recently done an assessment and has assessed them as endangered. So they're kind of in a state of flux right now. In 2003, though, the government of Nunavut was concerned about harvesting rates on this herd and also about drowning rates. So they started up a study to look at traditional knowledge of this herd, talking with elders, harvesters, and wildlife officers in both communities, so 30 people in total. And then there was a capacity shift. So a lot of this data remained unanalyzed until we started a collaboration with them in 2018. So they had done all of the interviews and the transcripts, and we came in to do the analysis. And the method that I used was with thematic analysis. So there's a really rigorous process to this, the 6 steps here, the familiarizing yourself with the data, looking at initial codes, searching for themes, reviewing those themes, and then naming the themes, and then finally producing the report. But I find that the most ambiguous part of this process is just how do you come up with those codes? So the 2 strategies I used was, first one is holistic coding, where I got to be a lot more familiar with the data and maintain the relationships between the different things that were being said. And then I also used in vivo coding, and that was to maintain the integrity of the traditional knowledge holders' voices. So out of that, I ended up coming up with this framework. And this framework helped me organize the data and make sense of it to get insights. So the first one you'll see here is the interdependence among everything. So that's really coming from that knowledge system that we're working in. And then moving into the community-based context, the observations of the knowledge is coming from Quillutuk and in Iqaluit, so Cambridge Bay. Then going further into that, what ended up coming up was this really important part about caribou culture, not the culture of the caribou, but of the people, so the people rely on the caribou. And then also having a really strong relationship with the land, and this acknowledgement that the weather and the environment are expected to change. There is also something about a caribou reality, so that the caribou are smart. They make their own decisions and have their own autonomy. Out of that, we got to learn some stuff about their behavior as it relates to migration. And the traditional knowledge holders are talking about how this caribou actually stays on Victoria Island and the mainland all year round. Just depends on a few different things, the amount. But what they saw was that it wasn't the entire herd that was migrating. And also in Quillutuk, they were saying that the caribou were migrating even further north than they had before and further south than they had prior to 2003. And in these maps, the one on the far side is the summer range, and then the one closer to me is the winter range. And that's, you can see that both, the island's the higher part, can't really see that, and then the mainland, so both are highlighted through both seasons. Also about sea ice. So they are indicating that when the sea ice forms later, the caribou were crowding that southern part of Victoria Island as they're waiting for the ice to form, and then moving further east towards Cambridge Bay. And when the ice did form later, some of the caribou just turned around and went right back inland on the island. So a lot more were staying on the island year-round when the ice was forming later. But when the ice formed early, a lot of the caribou did migrate down to the mainland. And what ended up impacting the rate of ice formation was due to winds and temperatures. So when it was windier and warmer, the ice formed later. And also that when the ice was forming later, there was a lot of caribou that were falling through the ice and drowning. Oh, moving caribou. So if we look at the maps, these are migration routes. The one on the far side is the fall, the one closer to me is the spring. And you can see in the fall one, there's 2 kind of groupings. There's one that's, the one that's right here, it's channeling around. So this is actually water right here. And it looks like they're avoiding the bay. So when it was open, going around it. And then also more channeling here. So if you go back to the spring, it's more spread out. So there's the difference there in the fall versus the spring. They were also saying that the caribou were mixing. And so the Dolphin Union caribou herd were mixing with the other herds around, the Bluenose East, Perry, and Bathurst. But it wasn't really clear to me whether or not they were talking about just intermingling, hanging out together, or if they were actually breeding together. And that is something that could be looked for further into, and it'd be really interesting because if they are interbreeding together, that could have an impact on genetics and then their behavior. So that's another question that we have. Abundance was really interesting. So if we look at this curvy thing. The pink ones were observations from Cambridge Bay, and the blue ones are from Kuluktuk. And they both agreed that long ago there are lots of caribou around. And then in the 1920s, 1950s, something happened and there weren't caribou around anymore. In Cambridge Bay, that decline, they associated it with a rain on snow event. The 1921s in Kuluktuk was associated with increased rates of drowning, but also the second one, the 1940s to 50s, was from a rain on snow event. And then they recovered. So in the 1970s to 80s, Kuluktuk started seeing lots of caribou, as many as they would have before. And then in the 80s to 2003 in Cambridge Bay, they were seeing a lot, as many as there were before. So there's a difference here in the 2003 dates. So in 2003 in Kuluktuk, there weren't caribou anymore. There are less caribou. They used to come onto the airport even. But in Cambridge Bay, they were still seeing lots of caribou. So there's some kind of difference happening there. And if we go to the maps, so these are hunting ranges. The further ones, the past hunting range, and then the 2003 hunting range. And I'm just gonna go to this one first. There's a really high concentration near the community in 2003 for Cambridge Bay. So that supports with them saying that there's lots of caribou around. They don't have to go far, they're just right there. Meanwhile, if you look at Kuluktuk's versus past and now, it's a lot smaller, it's shrunk. So this changes here, this Bathurst Inlet area, and it could be for a few different reasons, not just that the caribou aren't there, because before a lot more people would have lived down there, so if they moved into the community, but the fact that they're really close to town, so it goes along with that curve that I showed right before. And then we also got to talk about health, or they were talking about health. And in both communities, they're saying that they're seeing a lot of white dots in the meat, this consistent with a tinea cyst, and that a lot of the caribou were having these swollen joints or a watery joint, and that's more consistent with brucella, the description. Both communities also were talking about abnormal spleens, so like big spleens or shaped weirdly and being stuck to things, and this green pus under the skin. What was more just in Kuluktuk, they were saying that the lungs were getting stuck to the chest and that some caribous had rashes on their legs, so something that's consistent, that could be consistent with besnoidia. But in Kuluktuk, they're saying that the caribou are always getting sick in 2003, and that wasn't as expressed concern in Cambridge Bay. For body condition, both communities saw this general trend that the caribou were really fat in the summer and fall. The condition decreased a little bit in the winter, and then they were the skinniest in the spring, and then it recovered, that cycle. And that was mostly seen as impacts from heat, rain, and weather. And then for each community, Iqaluit, Cambridge Bay were focused a lot more on sex, so how the bull meat quality was during the rut. And Kuluktuk was focused on migration, so how the migration impacted body condition. If we look at where these communities are located, Cambridge Bay has easier access to the caribou during the time when they're rutting, but Kuluktuk has easy access to them right after they've migrated, so that makes sense. So if we look at that area of where we're seeing this knowledge, the differences in abundance, that insights into behavior and those health things, we see that it seems the caribou has shifted eastward sometime between the 1980s to 2003. And this really shows that this herd is responsive. It changes all the time. So if we just protect one part of that habitat, when they want to move somewhere else, they might not be able to. So going forward with research and protection, we really have to look at that entire home range. And also, both accounts weren't the same. The community accounts didn't exactly match each other. And that really showed that where the the traditional knowledge keepers are getting their knowledge from is really important, that place where they see the caribou. So when considering traditional knowledge for an entire Dauphin Union caribou range, we need to have observations from each community along the range to get a better snapshot of what's going on, because it's such a huge area to cover. So what's next? Just what I said. Those health snapshots, looking more into those health snapshots by community, and to understand how the caribou change over place and over time. So that being said, what I've been doing now is in 2018, I did 15 individual interviews with traditional knowledge keepers in Quillucktuk. And then later on the next year in 2019, I did some focus groups. And the focus groups were doing these more participatory activities. And the people that were involved in this were chosen by the Quillucktuk Hunters and Trappers organization, so the local Inuit authority, and also by who those participants that were already chosen suggested also to include in the study. And this analysis will be kind of similar to what I just did with the 2003 data, but we've also used a technique called the nominal group technique, which is a group consensus decision-making tool. So we've brought together people from the university, the government in Nunavut, and the Quillucktuk Hunters and Trappers organization to see what is actually coming out of these interviews, so that we make sure that we have the priorities of all the partners together. And then moving next, something that I've been developing now is just to look at more what the caribou need to live and thrive, and why do they need that. So the questions are, can this community knowledge from the 3 different communities that will be involved in this, if they can come together and see what's happening across the Dauphin Union caribou range, and if the mechanisms that we talk about can inform what habitat is needed from the past and going into the future as the land changes. And that'll be really important with this lens of climate change and things changing in the future. It's not designed yet, so I can't tell you how I'm going to do this, but in the future, you can find out. And the overall outcome of my research is really working to inform management plans and strategies for the Dauphin Union caribou herd, incorporating this place-based traditional knowledge about what's going on with the herd. Thank you.
So I think we can have questions, like 1 or 2 questions, if you're good with that.
Thank you. It was a wonderful talk. I've learned stuff and raised a whole bunch of questions in my mind. One of them is talking about going across the sea ice, how changes to the sea ice affect how they can migrate. Was there any discussion in your interviews or the 2003 interviews about icebreakers going through and cutting lines through the sea ice?
I just came down from a meeting in Cambridge Bay where we were talking about this. So there's a lot of government people there, and they're really concerned about mitigating the impacts on caribou, icebreaking on caribou, and on the community. So right now, they're in the process of making voluntary mitigation strategies, but it'll be super important in the future, because the migration of these caribou is really important. Why do they do it? I don't know, but they do it for some reason. So we have to protect it. Yeah. Right.
Hi, I'm Araleigh Cranch, and I'm going to talk about sea ice biogeochemistry tonight. How do I get to the next slide? Oh, I just had to do it twice. So when I say sea ice biogeochemistry, I mean dissolved inorganic carbon, which in a very basic sense is just the dissolved carbon dioxide gas. It's important though because when carbon dioxide gas dissolves in water, it can dissociate to carbonic acid, which acidifies oceans, which we're a little bit worried about with climate change. I'm also talking about salinity, which I think we all know what that is, but in sea ice it's highly related to dissolved inorganic carbon. And I'll be talking about chlorophyll concentrations, which are representative of the algal communities living on the bottom of the ice. Also, I will probably refer to dissolved inorganic carbon as DIC because dissolved inorganic carbon is a mouthful. So why does sea ice biogeochemistry matter? Well, there's a lot of it. According to the National Snow and Ice Data Center, sea ice covers about 25 million square kilometers in the winter, which is 2.5 times the land area of Canada. So when it melts in the spring, it brings a significant volume of sea ice melt to the surface layers of the ocean. And additionally, when it freezes, it rejects enough salt into the ocean to be credited by some scientists for global ocean currents. Sea ice is also thought to play a substantial role in greenhouse gas cycling, but the understanding of these processes is seriously lacking. This is mainly because the biogeochemical and physical properties of sea ice are extremely variable over space. And that makes it difficult to do climate modeling and carbon budgets that include sea ice because the ranges are just so big. So that's where I come in. My research aims to link the physical ocean environment, meaning current velocity and snow depth, to the biogeochemical properties of sea ice. If we can attribute the variability to something we know more about or something that we can measure remotely, we can more accurately estimate the contribution of sea ice to carbon cycling. So I also work near Cambridge Bay. I picked 2 sites based on a priori knowledge of the current velocities, Site A and Site B, very creative names. Site A was known to have a low current velocity, and Site B was known to have a faster current velocity. When we arrived at the sites, the differences were clear. Site A, the site we expected to be slow, had much less snow, about 15 centimeters on average, and the bottoms of the cores were visibly rich with algae. Site B, the site that we expected to be faster, had much more snow with about 26 centimeters on average and almost no visible algae. You can see the algae on the image on the left. That was definitely from Site A. To investigate the biogeochemistry, we took 15 DIC cores at each site. We then sectioned the top 10 centimeters, the middle 10 centimeters, and the bottom 10 centimeters of the core, and vacuum sealed them using a commercial meat sealer. We vacuum seal them, you can see the meat sealer there. We vacuum seal them to avoid equilibration with the surrounding air, which would lead to inaccurate carbon measurements. We do actually a lot to prevent these samples from interacting with air. First I vacuum seal them, then I melt them in the dark so what algae is there can't photosynthesize, and then I transfer them from their vacuum sealed bags into bottles using a peristaltic pump going from the bottom of the bag to the bottom of a bottle and overfilling the bottle. So there's a lot of work that goes into preventing interaction with room air. So in addition to those DIC samples, I also sampled for particulate chlorophyll 3 times at each site, so that's 6 times, which involves melting the bottom 10 centimeters of a core and then filtering that melt on a filter paper, which is then analyzed by my colleague in Manitoba, Laura Dahlman. We also took 3 temperature and salinity cores to calculate brine volume and ensure that the samples were representative. On the first day of my sampling campaign, we also froze current meters attached to wooden crosses into the ice. These meters were left for 5 days to measure current velocity to make sure that our a priori knowledge was correct. You can see the photo on the left there. That is the beginning of the removal process, which took a lot of augering, a lot of time, and a big team effort. to get those meters out and safely full of data. So I'd like to point out the figure on the right there. The axes are quite different. So the figure labeled logger A, the axis only goes up to 9 centimeters per second, whereas the graph labeled logger B, it goes up to 50 centimeters per second. So you can see logger A at site A recorded a very small average current velocity as opposed to site B. So our a priori knowledge was correct. So before I can talk about the biogeochemical results, I need to give a short lesson in sea ice formation. To simplify it, there are 2 main environmental pathways for the formation of ice. The first is formation in relatively calm waters, as is the case with Site A, or so we would assume. In calm waters, star-shaped or stellar crystals form over time. With little vertical mixing going on in the surface waters, it takes a while to get enough crystals to form in a given volume of water to actually get solidification, to actually get them bonding together and freezing, which usually happens on a particularly cold night. They're connected by needles. So a slower process for sure. The other environmental pathway for the top of the ice to form is in turbulent waters. Sorry. The same fragile ice crystals form, but they don't stay stellar for long. With the vertical mixing occurring in faster current conditions, there are significantly more crystals per unit volume, which causes the crystals to bump into each other and break off those stellar forms. And so you end up with equigranular, rounded crystals. And there's also just a lot more of them per unit volume. So this freezing is actually a cascading process by collision, and you get a lot more ice in a lot shorter amount of time. And then once there's enough, they bond pretty much on contact by adhesion and intercrystalline bonding. So that's about the first 10 centimeters. Now, I'd like to point out that ice likes to be pure in its crystalline form. So it rejects salts, it rejects dissolved gases to the best of its ability. However, when it's forming the top 10 centimeters there, it's not very good at it. So in faster conditions, you're going to trap more brine, and in slower conditions, you're going to trap less brine because the processes are slower. So kind of like magma solidifying in a rock, you get a better crystalline form. So the middle of the ice core is mostly uniform with brine pockets and channels. So brine is what the sea ice rejects to be pure. It's really salty, and it has most of the DIC that we find in sea ice in it. Now, the bottom of the ice cores, mostly that's influenced by the temperature of the water and the temperature of the air in equilibrium with each other. So if you have cold air, a warm ocean, the sea ice can only grow to a certain extent. So in slower conditions, you have less ocean heat flux, and also at our slower site, we saw less snow. So that ice should be thicker, and the bottom part should have grown faster, again, trapping more DIC and, well, brine in general. The flip side of that is a slower site would have less of a heat flux, and our slower site also had thicker snow. So we would expect that core to be shorter and take its time growing and have less DIC at the bottom. So how do my cores fit into the theory? Sorry, that's the wrong slide. Well, given that Site B has faster moving waters under its ice, we would expect an initial crystal formation by that fast collision process. Faster processes mean we trap more brine, and Site B absolutely did have significantly higher DIC concentrations in the top 10 centimeters when compared to Site A. So you can see there under the first pink arrow on both sides, I have the averages. So at Site B, it was 343 micromoles per kilogram, whereas at Site A, it was 281.6 micromoles per kilogram. Given that the processes are mostly uniform after the first 30 centimeters, we would expect that the middle sections would be very similar, which they absolutely were. They differed by only about 10 micromoles per kilogram, which is almost nothing in the scheme of things. And then again, at the bottom, we would expect Site A to be richer in DIC and also a longer core. That's the case. And Site B to have less DIC and a shorter core, which is also the case. So basically, my findings fit with the physical theories very well. But we're talking about biogeochemistry, so we can't completely forget about the biology. Last week, I received some preliminary results from my colleague in Manitoba. And the chlorophyll at site A, so the site that had more dissolved inorganic carbon in the bottom part of the core, had a lot more algae, just as we saw when we were actually at the sites. This means that algae is taking up carbon, so the difference between the two cores in the bottom 10 centimeters would actually have been greater than I measured before light was available for the photosynthesis to occur. So the differences based on the physical environment would have been greater. So in conclusion, I found two sites with very different physical characteristics and was able to relate those characteristics to the biogeochemistry of the ice using established theory in the literature. In doing this, I found a rationale to collect more data points in order to develop a quantitative relationship between the physical environment and sea ice biogeochemistry, which would reduce the range of end members in Arctic carbon budgets and climate modeling. And that's all I have today. Yeah?
What time of year were you taking this samples at?
May, early May. So the ice had not started melting yet, but there was definitely light for those little algae. Yeah?
What are stellar ice crystals?
So when ice forms, it is just the shape of the crystal. It looks like a star.
Oh.
Yeah. And that's kind of how they connect in the calmer situations, is they like hold star hands. I should have explained it like that. That would have been way more fun.
Okay, so you get to see some more carbon. So I'm going to talk to you about inorganic carbon cycling as well, but a bit of a different direction. You'll see Araleigh's in my list here. We work together, so we do have some commonalities between our work, but we work in very different settings near Cambridge Bay. So I'm going to talk about inorganic carbon cycling again, so the DIC that Araleigh talked about, or the carbon dioxide in the system, in a lake, river, coastal ocean continuum. So I'm looking at the land-sea connection and how we see carbon cycling across those three environments. And I'm going to talk about the carbon dioxide, but also about methane as well. A few key points to get us started. All natural waters play an important role in the global carbon cycle, both in the carbon dioxide part of that and in the methane part. They're both important greenhouse gases. And inland waters, or lakes, ponds, streams, are typically emitters of both of these greenhouse gases to the atmosphere. So they naturally release carbon dioxide and methane from the water into the air. Rivers and streams also deliver dissolved gases to the coastal ocean. So you have direct evasion from the water into the air, but you also have dissolved gas that can make it to the ocean as it travels from the land to the sea. And in the coastal ocean, you have a lot of variability. You can have the coastal ocean behaving as both a source or a sink of carbon dioxide and methane to the atmosphere. So in some areas, depending on the types of environments you might have carbon dioxide being released from the ocean moving into the air. In other areas, you might have uptake of CO2 from the atmosphere into the ocean, and you can have methane escaping from the water into the atmosphere. And this is particularly important in areas where you have rivers discharging material from the land into the sea. And I also want to point out that one of the big Things that I'm excited about in my work is working across 3 different settings, so a lake, a river, and an ocean. Typically, these environments are studied in silos, in isolation. Specialists in lakes will look at a lake environment in the carbon cycling. Oceanographers will consider the ocean. But more and more continuum studies across different settings are becoming more common, but it's still not the norm. Typically, you have experts in each of these environments, and you're not looking at the whole picture in one study. So what am I doing? In my dissertation, I want to employ an integrated approach to look at carbon cycling, both the CO2 and the methane, in these 3 different environments, with a focus on connections. How is the land connected to the sea? How is the lake connected to the river to the ocean? And how are all of these waters connected to the atmosphere? I want to know, where is the carbon coming from? What are the sources and what are the fluxes? So how does it move between these different environments, and also how does it interact? How does the interaction between the water and the atmosphere look? And in this presentation, I want to talk specifically about seasonal variations and give you a couple of examples from my work that I think showcase some of the most exciting things that I've found. I also work in Cambridge Bay, so you know where this is by now, but in Nunavut on Victoria Island, in the yellow star there. And I work in these 3 environments. So if you zoom into that yellow star, you can see what I've blown up on the map there on the left. Grainer Lake, which is the lake that I work in, it's connected to Cambridge Bay, which is the coastal ocean, via Freshwater Creek. And it's a short river. It's only about 4 kilometers between the outlet of the lake to the coastal ocean. So a little bit of a unique configuration, but it also is really helpful as a researcher because I can be based out of Cambridge Bay and access all of these environments really easily, sometimes even in the same day. I can do multiple different sites and see what's happening all at the same time. Why am I doing this? I hope that my results will have an impact in 4 different ways. Looking at establishing baseline conditions. So what does the carbon cycle look like right now? If we want to anticipate how climate change will impact this system, whether it's in terms of what type of gases might be emitted from a thawing landscape, or how the ocean might acidify with continued change, warming, and both additional carbon in the system, we need to know what it looks like right now. And then we can understand what are the vulnerabilities and what could change look like. It will provide a framework. So Araleigh introduced the concept of biogeochemical cycles. The carbon cycle is one of those, but there's a lot of other cycles as well. And so if we understand the carbon cycle, we can develop a framework that then we can compare with some of these other nutrients and compounds, what's happening. Hopefully it will be a constraint. So I'll produce one case study or one example that might be useful in bigger picture models, regional studies, carbon budgets, that sort of thing. And it could be an analog. So you can imagine working in this environment isn't easy, it's expensive, it's hard to get to. Sometimes it's not safe to work in certain areas, so you can't visit everywhere. And the Canadian Arctic is so vast, it's impossible to look at all of these systems. So if we can do a detailed study in one area and then perhaps apply that to other similar areas, that could be useful to other teams. How? So this is my 3rd year of NSTP and also fieldwork, so thank you. And that means, unfortunately, I won't be presenting here next year. I'll just get to heckle people. But I've gone up to the Arctic now 3 years in a row for more than 80 days of fieldwork across 4 visits. And during this time, I've collected time series data. But when I'm not there, the time series keeps going. And that's because our entire team contributes to going up there, collecting data at regular intervals, making it possible for us to look at the seasonal variations in these systems. We collect different types of data. Sensor data, so we actually take up instruments that we lower in the ocean water column, handheld instruments we can take in the freshwater environments, and we measure physical and chemical properties of the waters. And they're a bit different depending on if we're in marine or freshwater, but we collect things like temperature, pressure, conductivity or salinity, how much chlorophyll is in the water, that sort of thing, to give us hints about the biology. And we also collect discrete water samples. And this is, as Araleigh mentioned, really interesting because you need to collect these in a specific way so they don't interact with the atmosphere. You don't want them contaminated with the regular gases in the atmosphere. And so ideally we collect a water sample that never touches the atmosphere between when we get it out of the water and when we bring it into the lab. And in addition to collecting water samples for dissolved inorganic carbon and methane, we get things for other parameters. So dissolved nutrients, water isotopes, and all this information can support us in interpreting the carbon cycling data and understanding what that looks like over the course of the year. And the last point might be the most important. We do this via collaboration. So I mentioned that our team all contributes, but we also have 2 research technicians who are authors on this presentation who live in town, so they can access those sites all year round when we can't be there. And we work with other universities. And when you're working in these harsh environments, it's so important to do work and help each other so that we can all get this type of data to have these results that span more than just what one person can do on their own. Now I'll get into talking about seasonal variations, and that's going to be the focus of the rest of my talk. This is a really nice image that I really like and find inspiring from the land use plan by the Nunavut Planning Commission. And it shows the 6 Arctic seasons. And in each of these kind of slices of the pie, they've divided it up based on what's frozen and what's not. So when is the land frozen? When is the ocean frozen? When are those 2 different components thawed? And is it dark or light? Because all of these things influence the carbon cycling, I think it's really neat to apply this wheel and think about how does the carbon cycle look in the 6 Arctic seasons rather than the way that we typically divide up the year in Western science when we're trying to fit it to the 12 months that you can also see here. And I'm really interested in the transition between when everything is frozen to when everything is open. And so I focused a lot of my fieldwork on going up in May in the late spring before anything starts to thaw and waiting for spring melt and breakup to happen and sampling through that entire process until it's close to as open water and land as I can get in one field visit. And during that time, we have a couple of interesting things happen. The light's starting to return. The land ice and snow starts to melt first. We reestablish the connection between the land and the ocean by getting the rivers flowing, having the watersheds contributing again, and then that links up to the coastal ocean. And the sea ice breakup actually happens a little bit later. So you have almost 2 breakups, the land and then the sea. And then after open water season, you freeze up again and go through the winter. And in Cambridge Bay, there's no multi-year ice, it's all seasonal. So when we go into open water, everything is snow and ice free. I'm going to walk you through now the 3 environments that I work in and talk a little bit about some of the highlights in the data that I've seen so far. And then at the end, I'll talk a little bit about what's next. So first I'm going to start with the lake. This is an image that shows those same 3 features that were in the satellite image, the lake, the river, and the coastal ocean. But we're zoomed out. So now you can see the watershed that's associated with the lake, and it's shown with the red bolded line. And so this is a large area. It's about 1,500 square kilometers. The landscape is mostly low gradient, ponds, lakes. The flow can actually change directions over the year depending on how much water is there. But all of this area feeds into the lake, which then goes mostly into Freshwater Creek and then out into the bay. But this area doesn't contribute anything to the coastal ocean during certain parts of the year. During the winter, this is effectively disconnected because the rivers are completely frozen to the ground. There's no flow over the winter months. So in the open water season and during breakup and during freeze up, we have some contribution from the land, but then over winter, we separate the land and sea and then they're reestablished again the next year. The next slide I'm going to show you is going to be a series of profiles of dissolved oxygen at this star in the lake. And the reason I'm showing you dissolved oxygen is because it's something that we can easily measure in the field. The carbon dioxide and the methane, we have to bring the water samples back, we have to analyze them in the lab, that's a longer lead time. The feedback we get from measuring oxygen is immediate. And so when carbon dioxide and methane are high, oxygen is typically low, right? Those are complementary parameters. So when we see low oxygen, we know that's the time of year when we're typically having high greenhouse gas. And over the winter, the river freezes completely to the bottom, but the lake doesn't. It's got about 6 meters of water underneath a couple of meters of ice, and greenhouse gases can accumulate underneath that ice. And we lower the oxygen, we increase the CO2 and methane, and that's waiting there for spring to be released once we start to break up that ice. And this is what that profile looks like in the lake. So we've got surface of the lake up at the top, going down to about 8 meters depth, and then we've got dissolved oxygen. So you can see the orange and purple lines are in the summer. Well-mixed water column, it's churned around by lots of wind, it's really shallow, really well oxygenated, really nice water for fish to live in. And then after things freeze up, over the winter, progressively, that oxygen gets used up, and at the same time, we're accumulating carbon dioxide and methane underneath the ice. At the very bottom of this station, we actually enter the anoxic zone, so under 30% oxygen, and this is a really harsh environment to live in. At the top of this station, there's still enough oxygen to support life, but in some areas of the lake that are small and compartmentalized and shallow, all of the oxygen gets completely used up over the winter. And that's what I'm going to show you with this map. So this year when we went up, we did some activities where we actually went around the lake, drilled some holes, measured the oxygen, and collected samples for carbon dioxide and methane. And this map is showing you just one part of the lake. The outlet to the river is at the bottom here, and then this is sort of the southern part of the lake. And this is the station that you just saw the profiles from. That was the star on the bigger map that we saw. The size of the bubble and the number are telling you the percentage of dissolved oxygen saturation. So it goes from 0 to 100. And in that red area with the hatching, we see almost 0% oxygen. So that entire zone is this really neat compartmentalized area that goes completely anoxic over winter, and we have a massive accumulation of greenhouse gases under the ice in that area that then gets released during breakup. These are a couple of the methane results. So you can see I've just put them, same stations, I've just put the methane numbers in these call-out boxes. So if you just look at those numbers right away, you notice the methane concentration in that anoxic area is many orders of magnitude higher than the methane in the rest of the lake. And just to give you a feel for what the regular methane concentration in the lake would be over the summer, be about 30 to 45. And then in the ocean, it's 10. So this is a huge, huge amount of methane that's in that area. And when we see the initial breakup of the ice, that gets released both into the atmosphere directly from the water, but also moves into the river where it can go out to the ocean. So let's talk about the river a little bit more. This is just a quick image to show you that the river is relatively short. The lake outlet's at the top. It's about 4 kilometers down to the bottom where the river empties into the bay, just east of the town. And so when that pulse of water with low oxygen, high greenhouse gases is released from the lake, it enters that river and can very quickly make its way down and out into the ocean. The next 2 plots are 2 time series plots from the river station. So I have a regular station on the river that we try to sample in the past weekly, but now we've moved into every couple of days. And this year, when I was up there, I tried to sample it every other day. And this location corresponds with an Environment Canada gauging station. So we also have water flow and discharge from that river, and we can use that. We'll be able to use that to calculate total volumes of these gases going forward. So this is showing you date across the bottom. So starting in late May, breakup starts in early June, and then the concentration of the carbon dioxide, in this case, the dissolved inorganic carbon, up the y-axis. And so initial melt, you get a big pulse, and then that stabilizes around the 1500 later on once you've got open water and the system has kind of had that initial accumulation of gases move out and into the ocean. We see the same thing with methane. This is from 2018, and so the 3 first points here are when you have a channel that's just filled with meltwater, the lake hasn't opened up yet. All of a sudden we open up the lake and you get that huge methane pulse, which is coming out of that accumulation at the mouth of the outlet of the lake, just above the outlet of the lake where it enters the river. And then the methane is very low. So you can see, this is a nice visual to show you how much higher that concentration is than later on. I thought I'd show this because I think it's really neat. This is my favorite. This year when I was up there, I went for 5 weeks. I went at the end of May and I stayed until the end of June. And I visited the river almost every day. And I took a lot of images, looked at how change was happening and what the breakup looks like. So if you start in the top left, I'm standing on the bridge just downstream of my sampling station looking up towards the lake. You'll see the hill that kind of repeats in some of the images. And then I'm going back to this bridge. I have a few photos in and around the bridge almost every day and taking photos to see the progression of melt. In the beginning, you just have locally ponded snow melt water, which eventually ponds and expands enough that you develop a channel. But at this point, the channel's just draining snow melt. So this is low in greenhouse gases. It's just pure, almost pure water that's melted from the snow, moves into the channel, and moves down gradient towards the ocean. And then you get to a point where you actually melt enough to open up the lake. And that's when the volume of water dramatically increases in the river. And at that point, the melt is unstoppable. Within about a week, all of the snow and ice is completely gone. The energy of that, of water just melts everything else very quickly. And this moves out into the bay and it melts the sea ice as well. So the areas around the river are the first areas where the sea ice melts in Cambridge Bay during the spring. One of the things that I've done last year and this year with the help of people that live in Cambridge Bay and work as our research technicians and also Araleigh was 24-hour sampling campaigns, which were inspired by a paper out of Scotland by Waldron and others. And they were looking at active transformation of carbon in the river. So the idea that the river isn't just a passive conduit taking the carbon from land and dumping it into the sea, that processes are actually happening and you can see daily cycles reworking the carbon if you look at a high enough resolution. And so we wanted to repeat this year because last year we saw some interesting things. And this year we had a very lucky day and we started doing the sampling even though the lake hadn't opened up yet. And we were debating, do we do it, do we not? There's nothing really to see, it's just snow melt. And I said, you know what, I don't have that much time left in the field, let's do it anyway. And the day that we started to do it, started off normal, and then all of a sudden the lake opened up in the middle of our session. So we actually caught within 4 hours the opening up of the lake into the river, which is really exciting because we've never caught the pulse that early. So when we analyze the water samples for this, I expect we'll have higher concentrations of carbon dioxide and methane than we've measured in the river before, because we should get that very initial first pulse of greenhouse gases out of that area at the outlet of the lake. So this is really cool. And I've never seen this before in the literature. Maybe people have caught this before, but I have not seen a study like this. So this has the potential to be a really novel contribution of what that initial day looks like in the meltwater. And of course, all of this impacts the coastal ocean. So everything comes from the lake, goes into the river, flows out to the sea. And this is a nice picture that actually shows you how the river starts to melt the sea ice. Some of our stations are on here. So I'm going to talk about Freshwater Creek Station and also B1. So B1 is one of our kind of flagship stations. We do a lot of different measurements there, so we have a big suite of oceanographic information. We can actually look at B1 under the sea ice and see the pulse of the carbon dioxide and the methane go by as the breakup is happening. This is one example that shows that. So the top image is a time series at B1 in the surface water, so just a couple meters of water underneath the sea ice. And then you have the creek concentrations of DIC aligned with it, so same time axes. And you can see that that initial pulse of carbon dioxide causes a peak in the water underneath the sea ice. And the one thing that I really like about this image is that that peak is transient, and so if we don't do this time series sample, you can miss it. And it's significant. This peak contributes a lot of the carbon and the methane that we see on the whole annual cycle. And so if we don't include that peak, we miss out on a big chunk of what we're trying to measure. And you can also see another feature in the top plot there, where the sea ice actually melts and delivers a lot of fresh water right into the surface, and that actually decreases the carbon temporarily as well. So you've got this really dynamic kind of two parts to breakup that we can see at B1 in the surface water. And the methane shows the same thing. I don't have a plot for that, but we have a paper that is in preprint form that will be hopefully available soon that shows the methane peaks under the sea ice, and the same idea corresponding with the methane coming out of the river. So to wrap up, I hope that I've shown you that there is seasonal variation in all of these three settings. These are just a few examples. There's a lot more to show, but pick one storyline for today. And that breakup is particularly dynamic and important. And that's one of the times of year that is not only scientifically interesting, but also very beautiful. You get to see this full range of the environment looking in all different sorts of ways. And so I think it's really a privilege to be in the field at that time. That changes in the carbon dioxide and the methane cycling can be linked across the different environments. So if you were to consider each of these environments in isolation, you may not see those links, or it may not be obvious right away. So this continuum approach really highlights the connections. And time series is important. Without the time series sampling, we would miss a lot of these features. So going out and taking one or two measurements is sometimes the best you can do, because you can't just go to the Arctic whenever you feel like it most times. But then you do have to realize if that's what you're doing, you're not capturing the full range of variation. But I'm hoping a study like this will give context. So if someone goes out in open water season, they can say, well, I know I'm at this relative position within that seasonal cycle. I should expect this would be an underestimate. Or it will give you some context to position yourself. And then what's next? I've got many water samples to analyze, a lot of data analysis to get through, but I'm really, really excited to see especially what the samples from this year look like, because I think we have something that is potentially very unique. And with that, I will say thank you.
I think we'll probably go ahead and have Zoe's talk now and then have questions at the end. Does that sound okay? Yeah.
All right, so welcome to the third installment of Cambridge Bay from Brent's Lab. I'm Zoe, and I'll be talking about methane accumulation in Arctic lakes as well. So just a bit of background. I'm a new master's student in this lab, and I had the opportunity to do an exploratory field season, which really helped build the foundations of my master's work. So I'm very fortunate to have had this experience in Cambridge Bay. And as we saw earlier, the motive behind the project, so Brent's lab is mostly focused on oceanography and the marine systems. And we start to see the connection between marine hydrology with terrestrial hydrology in Sam's project. So my project goes more into the terrestrial hydrology in that I'm looking at lakes alone. So as I talked or said earlier, I'll be looking at methane accumulation in these lakes. But you might wonder, why do we care about methane accumulation? And the reason for that is methane is a greenhouse gas that is 30 times more potent than carbon dioxide, which means over 100 years, it is the, mess that up. Basically, it's the equivalent of 30 molecules of carbon dioxide in the atmosphere over the same 100-year timeline. And so that's really important to consider when we're looking at greenhouse gases and the greenhouse effect, because if more methane is in the atmosphere, it's going to amplify the greenhouse effect. So in the literature, recently, in the last 10 years, they've realized that fresh water is a major contributor of methane to the atmosphere. And in particular, Arctic lakes and the information regarding how much methane is released from them is lacking. So now that we care about methane, let's talk about how it accumulates. So this is a simple lake profile, and so lakes in the Arctic undergo freeze-thaw cycles, which means for part of the year they're frozen, part of the year they're unfrozen. And this sets up the opportunity for a phenomenon called thermal stratification. And so thermal stratification is where the water column divides into distinct layers. So the epilimnion or surface layer, and then the hypolimnion or bottom layer. And these distinct temperature differences are demarcated by the thermocline, which is the difference between these temperature layers. And these conditions set up ideal conditions for the production of methane. So this schematic kind of shows the yearly life cycle of a lake. So if we start in the late spring, early summer, we'll start to see a phytoplankton bloom. At this time, after the spring breakup, the water is homogeneous, so it has lots of nutrients, lots of oxygen, and as it starts to heat up in the water column, we start to see that thermal stratification. At this point, we can see a phytoplankton bloom because they've got all the things they need to photosynthesize. Nice conditions, sunlight, oxygen, and nutrients. However, once these phytoplankton start to die, they sink to the bottom of the lake, or the hypolimnion, and here, through the decomposition process, oxygen is consumed. So in the summer, we end up with a nutrient-depleted warm surface and an oxygen-depleted bottom layer of the lake. Now, these conditions are ideal for methogenic bacteria because they thrive in anoxic conditions because they respire anaerobically, which means in the absence of oxygen. So here, as they respire, they produce their carbon byproduct is methane. And because of the thermal stratification, the methane stays at the bottom of the lake because it can't break through the temperature gradient. In the fall, once the surface temperatures start to cool down, the cooler water molecules start to sink, and we do see some mixing. And then we get a layer of ice over the winter. And then we move back into spring where the ice breaks up. As the ice melts, that causes a change in density, which also turns it over, making it homogeneous once again. And so my sample collection was in May of 2019, which was about 2 weeks before the lake ice started to break up. So we had very stagnant water because depending on if your lake froze to depth or not, you could have a couple centimeters to a couple meters of water underneath the ice. So getting into my research, I have two project objectives at this point. The first is to generate a reference list of Arctic lake variables that are related to methane. And then the second is to determine which variable has the strongest influence on methane accumulation in these lakes, and try and use it as a predictor for lakes with high methane accumulation so that we can feed this into a model of if we know a certain characteristic is related to methane and it's easy to measure, we can use that as a predictor. So into the field sites and methods. So I was able to sample 33 lakes this season, which was awesome. The CBL lakes are just Cambridge Bay lakes, and those we sampled because we had information about the depth off from the start. And this was important because some of the lake ice got to 2 meters thick, so if we knew the lakes weren't that deep, there was no point in sampling them because they'd be frozen to depth. Additionally, I started looking at aerial images, and the next obvious feature to look at was lake area. So at the bottom here in the orange, I looked at what I classified as medium-sized lakes. Next, I thought it would be interesting to look at any of the topology of the landscape. So Mount Pelly is really the only feature that sticks out on the landscape. Everything else is flat. So I did a survey around Mount Pelly. And then I took some other samples further north. This is Grainer Lake where Sam did her samples. And then this is Lake Ferguson. This is not the ocean. And these they were just interesting to me. There was no feature that bound them together. So I just used my initials to label them. Sorry, vanity. So with lake selection, I used this remote sensing image, which was done in another project. This shows the Grainer Lake watershed. And this was important because they included the lake depths to a certain degree. So they measured things with lake depths of less than 2 meters, lake depths of 1 to 2 meters, and lake depths of greater than 2 meters. So I used this to kind of plan my sample sites because, again, the ice got very thick, so if we knew they were going to be shallow lakes, there was no point in sampling them. So to give you some context for the site setup and what we did at these sites, so we get to the GPS location, and then the first thing we did was drill a 2-inch auger hole through the ice. And if we punched through the ice, we would either hit water, which was great, and we could continue sampling, or we hit sediment, which meant the lake was frozen to the bottom, and now we have a dull auger. But if we hit water, that was great. And then we have a heated sled box, which is very fancy, and it acts as a portable lab for us. So we're able to do in situ and collect water samples from our sled box. It's great. So some more information about how the sampling works. So we used a submersible pump, which fits down this 2-inch auger hole, and it might not look like it, but in this image, it is about 10 feet long. And so we lower it to the depth we want it to sample at. Once it started pumping, we have this probe called the YSI, and it measures in situ values for temperature, pressure, conductivity, dissolved oxygen, turbidity, and, ooh, I'm missing one, pH. And then we also have a line breaking off here that's controlled by a valve so that we can also take water samples, which was important. So the water samples we took were dissolved inorganic carbon, total alkalinity, dissolved oxygen, oxygen-18 isotopes, nutrients, and salinity. And then the in situ measurements we got from the YSI were temperature, pH, conductivity, and dissolved oxygen. So lots of samples to process, still in the works of processing them. This image is me reading off basically live data from the YSI, which was really handy, as Sam pointed out, because we could get instant feedback on the dissolved oxygen in these lakes. So I'm still working through some of my samples, but I have preliminary results for something. So just to give you kind of an understanding of the breadth of variability in these lakes, this is a map showing the plotted depths. However, the average snow cover on these lakes was 17 centimeters, average ice thickness was 1.93 meters, average pH was 7.42, and the average lake depth was 5.15 meters. However, I had lakes as shallow as 1.86 meters that still had water at the bottom, and it says up to 14 meters. However, I actually don't know how deep that lake was because our measuring tape was not long enough. We also sampled 33 lakes, like I said, and I took 58 depth measurements. So I tried to do an under ice sample and then a bottom sample. And I did this to see if there was still stratification from the summer present under the ice. So the first result I want to talk about is dissolved oxygen. I plotted dissolved oxygen as a bottom measurement for this presentation because there wasn't as much stratification as I was expecting between the under ice and bottom measurement. And then I used 3 graduated proportions to show this. The first goes from 1 to just below 32% dissolved oxygen. And this is really important because fish require at least 30% dissolved oxygen to survive. So this can also be used in the reverse. So if we know that fish aren't present in a lake, we can likely assume that it also has very low dissolved oxygen. And so the variability here is huge. It goes from 1 to just under 94%. And in some of the surface measurements, the highest value was 111%. So it was super saturated with dissolved oxygen. The next variable I decided to map was dissolved inorganic carbon. And again, we see a lot of variability here. One thing I found interesting was moving down from the end of Lake Ferguson past Mount Pelly is all of these lakes have really low dissolved oxygen. Dissolved inorganic carbon, which I think they might be connected underwater, or underground, I'm not totally sure. But then we also see clusters of really high DIC as well. And then finally, I decided to map salinity as well. I found this interesting because freshwater lakes are generally not super salty. However, I had a couple lakes with relatively, considering these are freshwater, high salinity, so just under 2 PSU. And it was interesting because if I go, can I go back on this? Yes. I unfortunately lost this sample. The machine we used to measure DIC did not care for it. However, it has really high salinity, which could be used as a predictor for samples, as I will show you later. So one of the other relationships I wanted to look at was how dissolved oxygen varies with depth, because I thought there would be lower dissolved oxygen in deeper lakes, but I didn't find that. Instead, I found a relationship of higher dissolved oxygen with depth. However, this relationship is a little shady, but it's preliminary. Next, I decided to look at the relationship between dissolved inorganic carbon and lake depth, which again, we had decreasing dissolved inorganic carbon with depth. And then finally, just because I had plotted salinity, I looked at how salinity changes with depth as well, and noticed that these were also very similar. So then I decided to plot dissolved inorganic carbon against salinity to see how predictive, like how I could use these values to predict each other. And I think it's a pretty strong relationship, and it's pretty safe to say in that one site where I lost a sample, it likely had very high DIC. So future steps, I'm currently waiting on the analysis results for methane, oxygen 18, and nutrients. And hopefully with these, unfortunately I didn't have methane today, which was kind of the star of the show, but I'll be able to relate those back to the methane concentrations. I also want to modify some of the sampling procedures that were done in the 2019 field season and change them for 2020. And I also want to add additional lakes to sample. So in my the lakes that I was able to sample this year, I really went north and east of Cambridge Bay, but I'd love to go more south and more west and also get some lakes that are closer to the ocean. So in summary, there is a lot of variability in Arctic lakes, and understanding methane accumulation in Arctic lakes is important for improving the Arctic methane budget. And as this project progresses, hopefully further connections will be made between variables.
We're just gonna, anybody has a question for either of the last two speakers, I'll hand out the microphone.
Should I just sit?
Yes, you can sit. Anybody got a question for either of them? Yeah.
You don't want me to touch that, I've got
That's
a leg.
okay.
I'm just wondering, Samantha, yeah. As you probably know, the sewage pond for Cambridge Bay dumps pretty much, probably drains right into Freshwater Creek. How do you think that may or may not have affected your results and all the science that's happening in the ocean in Cambridge Bay?
Yes, so I didn't include the sewage in here, but the sewage pond is actually downstream of Freshwater Creek, so it discharges into the ocean. So all of the creek and the watershed is upstream of that. The sewage pond is kind of a surface wetland, and late in the summer they pump it out. It's usually a fairly short period of time, and we actually have done transects, not this year, but the previous 2 years, doing profiles including a site proximal to the sewage to look at if the nutrients coming out of there change the carbon cycling. So we've got a time series to look at that, and some of our colleagues at University of Manitoba are also looking at the biological aspect of how the sewage changes what's going on in the bay as well. So I didn't show it today, but we do have sewage data that I'm going to be incorporating into the carbon cycle and the carbon budget for the bay itself. Yeah.
Thanks.
Since Sam is
You showed that really nice satellite image of the sea ice melting at the mouth of the river. But your river broke up in basically one day, or the lake released in one day, and it went from nothing to this raging river. What happens to the sea ice on that day when all of a sudden you have this huge amount of water coming out?
So I also did take photos the other direction. The river, that kind of channel is established before, the beginning of that channel is established before the lake opens. So when you've got the meltwater draining out there, and I think it would actually be easier if I bring the image up again. You have a couple of things happening. So let's go to this one. Okay, so this is from June 21st. Don't ask me why I know that, but it is. And so this is about, during that year, this is about 2 to 3 weeks after breakup starts. So, and this is the same pattern that I've seen every time that I've been there. And so what happens is the melt, during that day when the lake opened up, this kind of channel or melt was out to about here. So it was still quite far. We have a transect that we call Creek Line that goes from here up towards the river, and we do our oceanographic measurements at all of those stations as well. And there was no way to get to the last 3 of those stations because the sea ice was too thin or gone at that point. So this is already established just with the snow melt. And then within a week of the lake opening up, you are getting out to this sort of thing. And people there say that this is where it melts first. So it seems like this is the way that it goes every year. But then I know the methane pulse looks really transient, but the pulse itself lasts, I would say, about half a week to a week. So we do see like a few days after it happens, if you go out 5 or 6 times, you will see elevated CO2 and methane. It's just that initial, what is your max going to be of the peak? But yeah, and you definitely, like the melt's taking advantage of any natural cracks or holes. And so as soon as you start getting water in this system, it starts moving really quickly. And so at first the river water is going on top of the ice, but then even before the lake opens up, you could see at the mouth of the river, like the ice was lifted up and water was going underneath it. And when you go out and measure out here, you're seeing fresh water at the top already, even though the gases aren't there yet, because you're getting some fresh water coming from the river, from other minor creeks, but there's also parts on the landscape where you can see water just draining from the snow down the side. And you can see it a little bit in this image, but you get the kind of moat around the edge of the ice, and water from the land just can run under there as well.
Thanks. Any other questions? Any questions for Zoe?
I've got to. Zoe, on your really nice schematic of how the lake turns over in the spring and the fall, how come you don't lose all the methane that you generated at the bottom of the lake in the summertime in the fall?
Thank you.
So good question. So from what I've read, you do lose some, but some still stagnates at the bottom. It depends on, I'm sure, other lake characteristics for how much is able to bubble out at that time, but some definitely stays. So. I guess.
Really short question. Is more methane formed while the lake is frozen?
I'm not totally sure about that either, because that's related to how much dissolved oxygen is present and whether, because there's also bacteria that consume methane, and then there's bacteria that produce methane. So there's a lot going on down there, which is always interesting. So this year I'd also like to take a sediment sample to determine conclusively what kind of bacteria are down there and in what proportions.
Any other questions? Okay, well, I'd like to thank all 4 of our speakers, all women, and lots of great work. And don't forget, if you apply for more NSTP money for next year, or when you're writing up your report for the work you did this year, make sure you acknowledge and give a link to this video. It's really helpful to anybody. Polar Knowledge would be interested. All right, and thanks everyone for coming out, and I look forward to our November speaker, Ryan Oliver, and there'll be details about his talk soon. We're waiting for his title and abstract. All right, thanks again. Bye-bye.